Welcome to our session on grid intelligence. We're discussing a new strategic point of view regarding the grid intelligence data and AI layer. How does this specific framework help utilities? Our focus is on the exclusive development and support of machine learning pipelines. The goal is to transform raw AMI telemetry into a predictive grid asset, making the data more actionable for the entire organization. Before we dive into the technology, let's look at the operational reality. So, what does a typical day look like for the teams on the ground?
It's a full schedule, starting with morning briefings at 6:30 a.m. and moving into field operations and technical support for AMI communication issues. Success for these teams means maintaining high installation accuracy, ensuring site safety, and reducing manual reads to improve overall network health.
How does data move from a single meter in the field to a business decision?
It's a journey that starts at the AMI head end, where networked meters transmit data for validation, estimation, and editing (VEE) within the MDM. From there, validated data triggers billing cycles in the CIS and coordinates field crews via work management systems. Finally, it integrates with GIS maps to drive high-level business intelligence and reporting.
Critical River has a specific blueprint for improving these operations. What are the main pillars of this strategy?
We focus on intelligent monitoring and integrated field operations. Key outcomes include delivering a unified AMI health dashboard as a single source of truth and using automated detection to track degradation before it impacts a customer's bill.
How can utilities specifically use their head-end system to improve these outcomes?
We use key operational indicators to detect early system degradation. We also apply intelligent logic to map failures geographically and optimize data recovery workflows, ensuring lost data is recovered without creating a massive backlog of exceptions.
What is the current state for most utilities, and why is it a problem?
Most operate in a complex mixed vendor environment with diverse meter families and legacy systems. Staff spend too much time manually interpreting fragmented alerts, which leads to operational friction, delayed issue detection, and unnecessary field dispatches.
Where are we trying to take them?
The future state is predictive. We want to transition from reactive alerts to early health prediction. By unifying key indicators and using auto backfill routines, we can improve billing stability and ensure field technicians have context-rich work orders for better fix rates.
What are the actual steps to reach that predictive state?
It requires 4 focused efforts: establishing standardized KPIs across workflows, deploying automation for triage rules, normalizing mixed device data for metadata consistency, and implementing governance frameworks with validation gates.
How does this look from a long-term technology roadmap perspective?
It's an evolution. It starts with migrating and replicating workloads to the cloud. Then we harmonize data to reduce silos and establish governance for a single version of truth. Only then can you fully realize advanced analytics, predictive analytics, and agentic AI.
As AMI scales to millions of endpoints, why do traditional methods fall short?
Traditional static rules simply can't handle the noise. AI and ML transform that noise into grid resilience by reducing manual data queues by 60 to 80%. During storms, we can reduce unknown meter counts from 16% to under 1%.
Let's look at the broader landscape of solutions. How does AI address operational latency?
We use tiered latency pipelines. Safety-critical events like high impedance faults are detected in minutes via a fast lane, while non-critical billing data flows through slow lanes. This ensures critical safety data isn't stuck behind routine processing.
This brings us to the core landscape of challenges we see across the industry. What are the most pressing issues?
They fall into three buckets: data quality, overwhelmed static rules and clock drift; operational latency, event storms flooding the head end; and governance, multiple ID systems, and no unified cross-commodity view.
On the data quality front, even a 1% error rate is a massive volume of bad data. How do we solve this?
For a utility with 1 million endpoints, that's 10,000 meters generating bad data daily. To solve this, we replace static thresholds with adaptive ML models that self-tune per meter class and season. We also use a phase balancing optimizer to identify the minimum reconnections needed to reduce peak loading. For example, from 94% to 71%, which removes data noise at the source. To address mixed firmware, we use automated schema normalization to identify firmware cohorts and gap-filling ML to infer insights for legacy meters.
What about when the grid fails during a crisis?
The challenge is that grid failure is top-down, but detection is bottom-up, waiting for individual last gasp messages through a disrupted mesh is too slow. To solve this, our hierarchical event processing engine infers outages for all downstream meters instantly. This reduces the unknown meter count from 16% to under 1% during a storm. For silent meters, we use ML gap filling with network topology to infer the status of silent meters with over 94% confidence, allowing for accurate crew dispatch without waiting for a direct signal.
Finally, how do we handle governance across different commodities and regulatory requirements?
Many utilities have electric, gas, and water accounts in separate systems, making analytics impossible. To solve this, we use ML-powered ID resolution to match these accounts using address and GPS data. Regulatory audits, whether for PUCT, TCEQ, or NERC-CIP, that used to take days of manual tracing are now instant queries because we use automated cryptographic lineage tags for every record.
Thank you for this deep dive. If you'd like to learn more about how we can help your organization reach this predictive future, please reach out to Aditya Deshmukh, @yahoo.com.